Space, a vast, infinite expanse that has captivated humanity's imagination for centuries. It is a place where the laws of nature as we know them are pushed, twisted, and sometimes completely broken. While we have sent probes across the solar system, landed on the moon, and unraveled the structure of galaxies millions of light years away, the truth is, our understanding of the universe is barely scratching the surface. Think about it. What if the answers to the biggest questions about existence were hidden just beyond the reach of our telescopes? What if space is keeping secrets that we may never fully uncover? In this video, we are diving deep into the 21st century's most perplexing cosmic enigmas, exploring 30 astonishing mysteries about the universe that even science cannot yet explain. From the origins of the cosmos to the eerie silence of extraterrestrial life, from the nature of dark matter to the edges of the observable universe, each question brings us closer to the edge of human knowledge and beyond. So, what else lies out there waiting to be discovered? Stick around as we embark on this incredible journey, tackling the mysteries that continue to baffle the brightest minds on Earth. Now turning to what came before the Big Bang, we begin with the understanding that the Big Bang is widely accepted as the leading theory for how our universe began. It describes a moment approximately 13.8 billion years ago when all matter, energy, space, and even time were compressed into an unimaginably dense and hot state, exploding outward to create the universe as we know it. But what about before this moment? That is where the mystery deepens. The very concept of before becomes tricky when time itself is thought to have started with the Big Bang. If time had a beginning, can we even talk about a before? Or does the question itself break down under the rules of physics? Some theories propose that the Big Bang was not the start of everything but rather one phase in a much larger cosmic cycle. According to the cyclical universe theory, our universe could be just one in a series of expansions and contractions, with big bangs and big crunches happening indefinitely across time. Others suggest the possibility of a multiverse, an infinite collection of universes existing alongside our own, each with its own set of physical laws and origins. In this scenario, our universe's Big Bang might have been triggered by some interaction between these alternate realms. Then there is the question of whether quantum mechanics could hold the key. Some physicists speculate that the origins of the universe might be found in quantum fluctuations, tiny, random changes in energy that could have sparked the creation of everything. These ideas challenge our fundamental understanding of reality, of time, and of existence itself. The implications are profound. If the Big Bang is merely one node in an infinite web of universes or cycles, what does that mean for our place in the cosmos? And if we could peer beyond that initial singularity, would we find the ultimate answers to why there is something rather than nothing? This question remains one of the most tantalizing mysteries in cosmology, leaving us to wonder if we are even capable of ever truly knowing what came before, or if such knowledge is forever beyond the grasp of science. Moving forward, we turn our attention to another cosmic enigma that continues to defy explanation, the perplexing nature of dark matter. Now turning to the mystery of dark matter, we encounter one of the most elusive components of our universe. Dark matter is the name given to an invisible substance that is believed to make up roughly 85% of the universe's total mass. Unlike the matter we see around us, stars, planets, and even ourselves, dark matter does not emit, absorb, or reflect light, making it completely undetectable by conventional telescopes. So, if we cannot see it, how do we know it exists? The evidence comes from its gravitational effects on galaxies and galaxy clusters. Observations show that stars on the outer edges of galaxies orbit much faster than they should, based on the visible matter alone. This unexpected speed indicates the presence of unseen mass dark matter exerting a gravitational pull. But what is dark matter made of? That is where the puzzle grows even more intriguing. Scientists have proposed several candidates, including weakly interacting massive particles, hypothetical particles that are thought to interact with regular matter only through gravity and possibly the weak nuclear force. Another possibility is actions, extremely light particles that could form a kind of invisible mist throughout space. Despite decades of research, no direct detection of dark matter has been achieved. State-of-the-art particle physics experiments, such as those conducted deep underground to avoid interference from cosmic rays, have been designed to capture the rare interactions that dark matter might have with ordinary matter, but so far, results have remained inconclusive. Some theories even suggest that our understanding of gravity might be incomplete, and what we attribute to dark matter is actually a sign that the laws of physics themselves need revising. Without a clear answer, dark matter continues to challenge our understanding of the universe's composition. Could it hold the keys to unlocking deeper truths about how the cosmos works? As we ponder this question, we move forward to explore an equally fascinating force that shapes the fate of the universe, dark energy. Now turning to the mysteries of dark energy, we delve into a phenomenon that is arguably even more perplexing than dark matter. While dark matter exerts gravitational pull to hold galaxies together, dark energy appears to do the exact opposite. It is driving the universe apart at an ever-increasing rate. This concept first emerged in the late 1990s when astronomers studying distant supernova made a groundbreaking discovery. They expected the expansion of the universe, initiated by the Big Bang, to be slowing down due to gravitational forces. Instead, they found that the expansion was accelerating as though some unseen force were pushing everything further apart. This force was named dark energy. What exactly is dark energy, though? Here lies one of the greatest puzzles of modern cosmology. It is invisible, untouchable, and does not interact in any way that we can directly observe. Yet it is estimated to make up nearly 70% of the total energy content of the universe. One leading theory to explain dark energy is the cosmological constant, first introduced by Albert Einstein over a century ago. According to this idea, dark energy could be a property of the vacuum of space itself, an inherent energy that remains constant as the universe grows. Another theory suggests it might be a dynamic field, often referred to as quintessence, which evolves over time and space, but testing these ideas is no simple task. The effects of dark energy are only observable on the largest scales in the cosmos, such as galaxy clusters and the rate of universal expansion. This makes direct experiments virtually impossible with our current technology. Nevertheless, researchers are tirelessly studying the cosmic microwave background radiation, large-scale galaxy surveys, and other relics of the universe's past to gain insights into this enigmatic force. What makes dark energy so important is its profound implications for the future of the universe. If its influence continues unchecked, it could lead to scenarios like the Big Freeze, where the universe keeps expanding and cooling until all stars burn out, or the Big Rip, where the accelerating expansion eventually tears galaxies, stars, and even atoms apart. Or perhaps dark energy might evolve in ways we cannot yet predict, altering the universe's destiny entirely. The study of dark energy poses some of the most profound questions in physics, challenging us to rethink not only the universe's fate but also the fundamental nature of reality. As we grapple with this intangible force, another timeless question lingers in our minds. Are we alone in the universe? As the next challenge unfolds, we confront one of humanity's most enduring questions. Are we alone in the universe? When contemplating this mystery, the sheer scale of the cosmos is both humbling and awe-inspiring. With hundreds of billions of galaxies, each containing hundreds of billions of stars, the possibility of planets like Earth existing elsewhere seems not just plausible but almost inevitable. Yet, despite the numbers being in favor of extraterrestrial life, we still have no definitive evidence of its existence, and this gives rise to the Fermi Paradox. The Fermi Paradox asks a simple yet profound question. If the universe is so vast and ancient, and if intelligent life is likely to exist, why have we found no signs of it? Where are all the alien civilizations? Various hypotheses attempt to address this paradox. One suggests that intelligent life is exceedingly rare, perhaps hindered by the extreme improbability of complex life developing. Another posits that advanced civilizations may have self-destructed before achieving interstellar communication. Alternatively, the silence might be because extraterrestrial civilizations are deliberately avoiding contact, or because their signals are simply undetectable with our current technology. In our search for answers, scientists have turned to advanced methods of detecting biosignatures, chemical markers that indicate the presence of life, and technosignatures, which are signals or structures that suggest advanced technology. Missions like the Kepler and TESS space telescopes have already identified thousands of exoplanets, some located in the so-called habitable zones, where conditions might allow liquid water to exist. Meanwhile, researchers are studying exoplanet atmospheres for gases like oxygen, methane, and carbon dioxide, which could indicate biological activity. Additionally, projects like SETI, the search for extraterrestrial intelligence, continuously scan the cosmos for radio signals or other forms of communication from intelligent beings. However, the absence of evidence is not necessarily evidence of absence. The universe is overwhelmingly vast, and our technology is still in its infancy when compared to the distances and timescales involved. As we improve our instruments and refine our methods, the possibility of uncovering the truth about extraterrestrial life remains tantalizingly within reach. The question of whether we are alone is not just about the existence of aliens. It challenges us to redefine our place in the cosmos and what it truly means to be human. As we peer deeper into the universe for answers, another fundamental mystery comes into focus: the very nature of time itself. Moving forward, we delve into one of the most profound enigmas of the universe: the very nature of time. Time as we experience it feels constant, ticking forward in a steady rhythm. Yet, according to Albert Einstein's groundbreaking theory of relativity, time is far from uniform. It can stretch, compress, and even warp, depending on the presence of gravity and the speed at which one is moving. For example, near a massive object like a black hole, the intense gravitational pull causes time to slow down, a phenomenon known as time dilation. To an observer far from the black hole, a clock placed closer to it would appear to tick more slowly. This astonishing concept has been confirmed through experiments and has profound implications for our understanding of reality. But what exactly is time? Is it a fundamental aspect of the universe, or is it merely a construct of human perception? Some physicists argue that time might not even exist as we imagine it, that it could be an emergent property arising from more fundamental physical laws. Others debate whether the flow of time is real or just an illusion created by our consciousness. The arrow of time, which dictates that events move irreversibly from the past through the present to the future, appears to align with the second law of thermodynamics, where entropy or disorder always increases. But why does time seem to flow in only one direction? Could it ever be reversed? In theoretical physics, the concept of time travel emerges from the possibility of bending space-time itself. Wormholes, if they exist, might serve as cosmic shortcuts that connect two distant points in space-time, potentially allowing travel not only across space but also through time. However, these ideas remain speculative, and even if time travel were theoretically possible, it would raise paradoxes that defy our current understanding of cause and effect, such as the classic grandfather paradox, where altering the past could prevent one's own existence. Time, then, remains one of the greatest riddles of the cosmos, intertwining physics with philosophy and challenging our very perception of reality. As we grapple with these mind-bending questions, the mysteries of what lies beyond the observable universe beckon us to look even further. Now turning to the mysteries that stretch beyond our cosmic horizon, we arrive at the question, what lies beyond the observable universe? The observable universe is defined by the distance that light has been able to travel since the beginning of time, about 13.8 billion years. Because the speed of light is finite, this creates a boundary, a spherical region of space from which we can detect information like light, radiation, or other signals. But beyond this limit, the universe doesn't simply end, it continues. The big question is, what exactly lies out there? One possibility is that the universe is infinite, extending forever in all directions, filled with countless stars, galaxies, and possibly other phenomena we can't yet imagine. Another idea is that beyond the observable universe may lie regions completely different from what we see. A multiverse where different physical laws, constants, or even dimensions could exist. Some theories suggest that our universe might be just one of innumerable bubbles within a larger multiverse structure. But how could we ever confirm what exists beyond this boundary? The challenge lies in the fact that light from these regions will never reach us, making direct observation impossible. Scientists have proposed indirect methods, such as looking at subtle patterns in the cosmic microwave background, the faint afterglow of the Big Bang, for clues about what might lie beyond. However, even these approaches remain highly speculative. If the multiverse theory is true, it raises profound questions about our place in the cosmos and the nature of existence itself. Are we living in just one version of countless possible universes? Could copies of our galaxy, or even ourselves, exist somewhere out there, shaped by slightly different conditions? These ideas are not only difficult to test, but also stretch the limits of human imagination. While the observable universe has revealed breathtaking insights about the cosmos, what lies beyond remains shrouded in mystery, a vast unknown that continues to inspire both awe and curiosity. As we probe deeper into these questions, we find ourselves drawn to another cosmic enigma, the very existence and role of black holes in the universe. Now turning to the enigma of black holes, these cosmic phenomena are among the most puzzling and captivating objects in the universe. A black hole forms when a massive star exhausts its nuclear fuel and collapses under its own gravity, compressing all its mass into an incredibly small space known as the singularity. This creates a gravitational force so immense that nothing, not even light, can escape once it passes a boundary called the event horizon. But why do black holes exist in the first place, and what role do they play in the grand architecture of the cosmos? Black holes are not just destructive voids, they are key players in shaping galaxies. At the center of most galaxies, including our own Milky Way, lies a supermassive black hole millions or even billions of times the mass of our Sun. These colossal entities influence the motion of stars and gas, helping to regulate the growth and evolution of their host galaxies. Yet, despite their importance, black holes remain one of the greatest challenges to our understanding of physics. They merge two seemingly incompatible theories: Einstein's general relativity, which explains gravity and the large-scale structure of the universe, and quantum mechanics, which governs the behavior of the tiniest particles. At the singularity, the known laws of physics break down, exposing gaps in our understanding of the cosmos. Studying black holes not only helps us explore the limits of space and time, but also pushes the boundaries of human knowledge toward a unified theory that could reconcile these two fundamental frameworks. As scientists continue to observe black holes, particularly through groundbreaking detections of gravitational waves from black hole mergers, we are unraveling new details about their formation and behavior. Despite these advancements, black holes remain a profound mystery, an intersection of the known and the unknown, reminding us of how much we have yet to discover. With this cosmic enigma in mind, we now shift our focus to an even deeper question: what happens inside a black hole? Now turning to the heart of the mystery, what happens inside a black hole? At their core lies the singularity, a point where the laws of physics as we know them cease to apply. Here, all the mass of the black hole is compressed into an infinitely small space, creating a region of infinite density. Surrounding this is the event horizon, the boundary beyond which nothing, not even light, can escape. Once an object crosses this point, it is lost to the black hole forever. But what truly occurs beyond the event horizon remains one of the greatest puzzles in astrophysics. Inside a black hole's event horizon, space and time are thought to become so distorted that they switch roles. Time, as we understand it, flows toward the singularity like a one-way street, making escape fundamentally impossible. The closer you get to the singularity, the more extreme the conditions become. Gravity is so intense that it stretches and compresses anything in its path, a process often described as spaghettification. Yet, even this vivid concept only scratches the surface of what might be happening inside. The singularity not only defies our understanding of physics, but also represents a profound clash between two foundational theories. General relativity, which governs massive objects like black holes, predicts the singularity's existence. On the other hand, quantum mechanics, which explains the behavior of particles at incredibly small scales, cannot reconcile with the infinite density and gravity at the singularity. This conflict exposes a significant gap in our comprehension of the universe and points to the need for a unified theory that can explain both the cosmos and the quantum realm. Could new physics emerge from studying these phenomena? Some theories suggest that the singularity might lead to another universe, or that black holes could even serve as gateways to other dimensions. However, without direct observation, these ideas remain speculative. What is certain is that black holes challenge the very fabric of our understanding of reality, pushing us to question the limits of what we know. As humanity continues to probe these mysteries, black holes remain both a source of wonder and a reminder of the infinite unknown. With this journey into the depths of a black hole in mind, it is time to expand our gaze and ask an equally mind-bending question: what is the ultimate fate of the universe? With the next phase of the journey in sight, we now ponder one of the most profound questions in cosmology. What is the ultimate fate of the universe? As vast and eternal as the cosmos seems, scientists are certain that it has a finite destiny. At the heart of this enigma lie three dominant theories: the Big Freeze, the Big Crunch, and the Big Rip. Each offers a dramatically different vision of how the universe could meet its end. The Big Freeze suggests that the universe will continue expanding forever. Over billions upon billions of years, galaxies will spread further apart, stars will exhaust their fuel, and temperatures will drop to near absolute zero. In this scenario, the cosmos becomes a dark, cold, and lifeless expanse, a chilling fate where all activity ceases. On the other hand, the Big Crunch envisions a reversal of the expansion. Here, gravity could one day overpower the force driving the universe's growth, causing everything to collapse back on itself. Galaxies, stars, and planets would be drawn together in a violent implosion, potentially resetting the universe to a state similar to its origins. Some even speculate this cycle could repeat endlessly, leading to an eternal series of expansions and contractions. Then there is the Big Rip, a more unsettling possibility tied directly to the mysterious force known as dark energy. This theory proposes that the accelerating expansion of the universe, driven by dark energy, might eventually tear apart galaxies, stars, and even atoms themselves. If true, this catastrophic scenario would dismantle the universe at its very foundations, leaving behind nothing but scattered particles. Dark energy, which makes up a significant portion of the universe, plays a central role in determining which of these fates awaits us. Its properties, still poorly understood, hold the key to whether the cosmos will freeze, crunch, or rip apart. Studying dark energy is therefore essential to unraveling this cosmic mystery. What makes this question so captivating is its sheer scale. Determining the universe's fate forces us to confront not just the limits of existence, but also the nature of time and space itself. Each of these theories challenges us to imagine the incomprehensible, a future so distant that it transcends human understanding. While scientists continue their quest for answers, one thing is clear: the story of the universe is far from over, and its final chapter is a puzzle that may take generations to decode. As we marvel at these possibilities, it leads us to another enduring mystery. How do galaxies, those magnificent islands of stars, come into being? As the next challenge unfolds, we delve into the intricate process of galaxy formation, a phenomenon as mesmerizing as it is mysterious. Galaxies, the colossal collections of stars, gas, dust, and dark matter, did not always exist in the universe. Their origins trace back to the early moments after the Big Bang, a time when the cosmos was filled with a hot, dense soup of particles. In this primordial universe, minute fluctuations in density acted as seeds for galaxy formation. Over millions of years, these tiny irregularities began to amplify under the influence of gravity. Clouds of gas and dark matter started to collapse, forming the earliest structures that would eventually become the galaxies we observe today. From these ancient beginnings, galaxies evolved into the stunningly diverse shapes we now see: spirals with gracefully curving arms, elliptical galaxies shaped like soft glowing ovals, and irregular galaxies that defy neat classification. Yet the story of how these forms emerged remains incomplete. Scientists know that factors like rotation, the presence of dark matter, and interactions between galaxies play a role, but piecing together the full picture is a challenge. For example, when galaxies collide or merge, the impact can dramatically reshape their structure, sometimes forming entirely new configurations. These interactions are thought to influence star formation and even the growth of supermassive black holes at galactic centers. Despite these insights, profound questions remain. Why do some galaxies form as spirals while others become ellipticals? What mechanisms dictate the pace of star formation within them? And how does the mysterious dark matter, which neither emits nor reflects light, govern their evolution over billions of years? These uncertainties leave researchers continually refining theories and developing sophisticated simulations to better understand the forces at play. Each discovery brings us closer to unraveling the complexities of galaxy formation, but much like the universe itself, the subject seems endlessly vast. As we ponder the birth and evolution of galaxies, another question naturally arises: what lies at the heart of our own galaxy, the Milky Way? Now turning to the heart of our own galactic home, we find one of the most captivating mysteries of the cosmos: what lies at the center of the Milky Way. At the core of our galaxy resides an extraordinary object known as Sagittarius A*, a supermassive black hole with a mass roughly 4 million times that of our Sun. This behemoth of gravity exerts an immense influence on the stars and gas that orbit within its vicinity, creating a dynamic and turbulent environment. But how was this enigmatic presence discovered? Decades of observations revealed that stars near the galactic center exhibit bizarre, high-speed orbits, moving as if being flung around an invisible, incredibly massive object. These motions provided compelling evidence for the existence of a supermassive black hole, a finding that has since been confirmed through advanced imaging techniques. Despite this remarkable discovery, Sagittarius A* remains shrouded in questions. For one, it is surprisingly quiet for such a colossal black hole, emitting relatively low amounts of radiation compared to others of its kind. Scientists are still trying to understand why it appears to be in a dormant state, consuming only minimal material from its surroundings. Occasionally, Sagittarius A* emits sudden bursts of energy, but the mechanisms behind these flares are not yet fully understood. What causes these outbursts, and could they hint at dynamic events occurring deep within this gravitational powerhouse? Its role in shaping the Milky Way also raises fascinating questions. Does it influence the formation of stars? How does it interact with the galaxy's spiral arms, its vast reservoir of gas, and the mysterious presence of dark matter that surrounds us? Understanding Sagittarius A** not only provides insight into our home galaxy, but also sheds light on the nature of supermassive black holes across the universe. These cosmic giants are believed to exist at the center of most galaxies and may even play a crucial role in regulating their growth and structure over billions of years. Yet, the precise nature of this relationship remains one of astronomy's great puzzles. As researchers continue to observe Sagittarius A* using cutting-edge observatories both on Earth and in space, each data point fuels our quest to decipher the mysteries locked within. And while the secrets of our galactic core are slowly being revealed, they also ignite curiosity about the larger structure of the universe. With that, we turn our gaze outward, exploring the question of why the universe itself is structured the way it is. Now turning to the vast expanse beyond our galaxy, we encounter one of the most profound and complex questions in cosmology. Why is the universe structured the way it is? When we look at the cosmos on a grand scale, we see an intricate web of galaxy clusters, superclusters, and cosmic filaments stretching across immense distances, separated by vast, seemingly empty voids. This large-scale structure is not random, but instead shaped by forces that have been at work for billions of years, creating patterns and formations that both amaze and perplex scientists. At the heart of this cosmic arrangement lies the influence of two powerful factors, gravity and an unseen substance known as dark matter. Gravity, the fundamental force that draws objects together, acts like a cosmic sculptor. Over time, it pulls galaxies into clusters and binds these clusters into even larger superclusters. But what gives these structures their specific shape and distribution? This is where dark matter enters the picture. Dark matter, though invisible and undetectable by conventional means, makes up the majority of the universe's mass. Its gravitational pull provides the scaffolding on which galaxies and their clusters form. Computer simulations of the universe's evolution show that without dark matter's influence, the intricate web-like structure of the cosmos simply would not exist. Yet, the uneven distribution of matter remains a lingering mystery. Why do some regions of space become dense with galaxies and clusters, while others remain vast, empty voids? Scientists believe this unevenness can be traced back to the earliest moments after the Big Bang, when minute fluctuations in the density of matter were amplified over time by gravity. These initial irregularities, imprinted on the universe like a fingerprint, set the stage for the cosmic architecture we see today. However, the exact mechanism behind these primordial fluctuations and their role in shaping the universe is still not fully understood. Adding to the enigma is the role of other factors such as dark energy, the mysterious force driving the accelerated expansion of the universe. As space itself stretches, the distances between these structures grow, and their future evolution becomes increasingly uncertain. Will superclusters eventually separate so far that they drift into isolation? Could the cosmic web's intricate patterns be erased by the relentless force of expansion? Understanding the large-scale structure of the universe is like piecing together a puzzle on the grandest possible scale, with many of the key pieces still missing. Each discovery not only deepens our understanding of the cosmos, but also raises new questions about the forces and phenomena that shape it. As we continue to map the cosmic web using advanced telescopes and simulations, we edge closer to unlocking these secrets. And as we ponder the mysteries of the universe's structure, our journey naturally leads us to the next cosmic frontier, where we explore the perplexing phenomenon of fast radio bursts and their elusive origins. As the next challenge unfolds, we encounter the captivating mystery of fast radio bursts, fleeting yet immensely powerful signals of radio waves coming from distant galaxies. These bursts, lasting mere milliseconds, pack an incredible amount of energy, sometimes equivalent to what our sun emits in an entire day. First discovered in the early 2000s, fast radio bursts, often referred to as one of the most enigmatic phenomena in astronomy, have since intrigued scientists worldwide. The origins of these bursts remain a puzzle. Some researchers suggest they could be linked to cataclysmic events, such as the collapse of massive stars into neutron stars or the merging of neutron stars into black holes. Others propose that highly magnetized neutron stars, known as magnetars, might produce these bursts during violent outbursts of energy. Yet, the possibility of artificial origins, perhaps signaling advanced extraterrestrial civilizations, cannot be entirely ruled out, adding an extra layer of intrigue to the mystery. What makes fast radio bursts particularly fascinating is their unpredictable nature. Unlike pulsars or other known cosmic phenomena, these bursts do not occur at regular intervals, making them incredibly challenging to detect and study. However, advancements in radio telescope technology, such as the use of wide-field arrays and fast scanning methods, have enabled astronomers to capture more of these bursts in recent years. The discovery of repeating fast radio bursts, which originate from the same cosmic location, has been especially groundbreaking, offering scientists critical clues about their nature. By studying the characteristics of these bursts, including their dispersion, researchers can glean valuable information about the material they travel through on their journey to Earth. This data not only helps us understand the environments near the sources of these bursts, but also offers insights into the large-scale structure of the universe itself. Despite these advances, the precise mechanisms driving fast radio bursts and the reasons for their immense energy remain shrouded in mystery. As scientists continue to refine detection techniques and build more sensitive telescopes, the hope is that we will one day uncover the true nature of these bursts. Whether they originate from exotic cosmic events or perhaps even from intelligent life, fast radio bursts remind us of the vast unknowns that still surround us. And just as we marvel at these fleeting signals from the distant cosmos, we now turn to another profound question. What are wormholes, and do they exist as gateways through space and time? Now turning to the intriguing concept of wormholes, we venture into one of the most captivating ideas in theoretical physics. A wormhole, sometimes referred to as an Einstein-Rosen bridge, is essentially a hypothetical tunnel connecting two separate points in spacetime. Predicted by solutions to Albert Einstein's equations of general relativity, these cosmic shortcuts have ignited the imagination of scientists and science fiction enthusiasts alike. Imagine being able to traverse vast distances across the universe in mere moments or even journey through different points in time. While the idea sounds thrilling, the reality of wormholes, if they exist, is far more complex and elusive. To understand wormholes, it helps to picture spacetime as a two-dimensional sheet. A wormhole can be visualized as bending this sheet so that two distant points touch, creating a direct passage between them. If such a phenomenon exists, it could revolutionize our understanding of travel and communication, eliminating the need to traverse the unimaginable expanses of the cosmos the hard way. The potential implications are staggering. Interstellar exploration could become almost instantaneous, and humanity's reach could extend to the farthest corners of the universe. However, wormholes as we currently understand them are purely theoretical. Scientists debate whether they could even form naturally or if they might require exotic matter, a substance with negative energy density, to stabilize and prevent them from collapsing. The challenge lies in the fact that we have yet to observe any evidence of wormholes in the cosmos, and detecting them, if they exist, would require technological advancements far beyond what we currently possess. Moreover, even if wormholes are proven to exist, they bring with them a host of mind-bending questions and potential paradoxes. Could traveling through a wormhole allow for time travel? And if so, what happens to causality, the idea that cause precedes effect? Could wormholes be traversed safely, or would immense gravitational forces destroy anything attempting to pass through? These are just a few of the profound mysteries that continue to puzzle scientists. Despite these challenges, the notion of wormholes remains a tantalizing possibility. Researchers in fields like quantum mechanics and string theory are exploring whether such structures could arise from the fabric of space-time itself. Theoretical advancements, coupled with future breakthroughs in observation and experimentation, may one day provide definitive answers. As we ponder the existence of wormholes and their potential to reshape our understanding of the universe, we are reminded of how much there is yet to uncover about the cosmos. Moving forward, let us explore another fundamental question that continues to defy easy explanation. What is the true nature of gravity? Now turning to the profound question of gravity, we delve into one of the most fundamental and yet enigmatic forces shaping the universe. Gravity, the invisible force responsible for keeping planets in orbit and giving weight to objects, has been a cornerstone of our understanding of physics for centuries. Isaac Newton first described it as the force that attracts two bodies toward each other, but Albert Einstein revolutionized this idea with his theory of general relativity. He proposed that gravity is not a force in the traditional sense, but rather the result of massive objects curving the very fabric of space-time. This groundbreaking perspective not only explained phenomena like planetary orbits, but also predicted extraordinary features of the cosmos, such as black holes and the bending of light around massive objects, known as gravitational lensing. Yet, for all its successes, gravity remains a puzzle at the smallest scales. While general relativity provides a comprehensive description of gravity on a cosmic level, it does not align with the principles of quantum mechanics, the framework that governs the behavior of particles on an atomic and subatomic scale. This disconnect has left physicists searching for a unified theory that merges these two pillars of modern science into one coherent explanation, often referred to as a theory of everything. One of the major challenges in this quest is that gravity is exceedingly weak compared to the other fundamental forces, such as electromagnetism. Think about how a simple magnet can lift a paperclip off the ground despite the entire Earth's gravitational pull acting in the opposite direction. This disparity makes it incredibly difficult to study gravity at the quantum level, where the effects are so faint that they become almost impossible to observe. Several ambitious theories have been proposed to bridge this gap. String theory, for instance, suggests that all particles are tiny vibrating strings, and that gravity emerges from the vibrations of specific types of strings. Another approach is loop quantum gravity, which attempts to quantize space-time itself, breaking it down into discrete, indivisible units. While these ideas are intellectually fascinating, they remain largely theoretical, as the technology needed to test them is still far beyond our reach. Moreover, gravity continues to present mysteries even on larger scales. Scientists have observed that galaxies rotate in ways that cannot be explained by the visible matter they contain, leading to the hypothesis of dark matter. Could revisiting our understanding of gravity offer an alternative explanation to the dark matter dilemma? Some researchers have suggested modifications to Einstein's equations that might account for these anomalies without invoking unseen matter, but these ideas remain highly debated. The true nature of gravity holds the key to unlocking some of the deepest questions about the universe, from the origins of the cosmos to the fate of black holes. As physicists strive to reconcile gravity with quantum mechanics, they edge closer to a more complete understanding of the universe's fundamental workings. And as we wrestle with these profound questions, it only fuels the curiosity that drives scientific exploration. Now, let us examine another cosmic enigma. Can humanity ever achieve faster than light travel? As the next challenge unfolds, we turn our attention to the tantalizing question: can humanity ever achieve faster than light travel? The speed of light, an astonishing 300,000 kilometers per second, is not just fast, it represents the ultimate speed limit of the universe as dictated by Einstein's theory of relativity. According to this theory, as an object approaches the speed of light, its mass increases exponentially, requiring infinite energy to reach that elusive barrier. This makes faster-than-light travel seem impossible within the known laws of physics. Yet, this limitation has not stopped scientists and dreamers from exploring ways to bend or even break these cosmic rules. One of the most intriguing ideas is the concept of a warp drive, popularized by science fiction but rooted in theoretical physics. Inspired by Einstein's equations, a warp drive would work by compressing space ahead of a spacecraft while expanding it behind, creating a bubble of spacetime that allows the ship itself to remain stationary. In essence, this would move the universe around the spacecraft rather than forcing the spacecraft to move through it. While this idea sounds promising, current calculations suggest that the energy required to create such a bubble would exceed what the entire sun produces in a year, making it a distant dream for now. Another speculative avenue involves wormholes, theoretical shortcuts through spacetime that could connect distant parts of the universe. These have been predicted by Einstein's equations but remain purely hypothetical, with no evidence yet that they exist or could be safely traversed. Even if wormholes were real, they might require the use of exotic matter with properties that defy the known laws of physics to keep them stable. The challenges of both discovering and harnessing such phenomena remain monumental. Scientists have also proposed manipulating the quantum realm in search of solutions. Certain interpretations of quantum mechanics suggest phenomena like quantum tunneling, where particles can seemingly bypass obstacles at incredibly small scales. While fascinating, scaling such effects to the level of interstellar spacecraft currently lies far beyond our technological capabilities. The idea of faster-than-light travel also raises profound questions about causality and the nature of time itself. If we were to exceed this cosmic speed limit, could we inadvertently disrupt the sequence of cause and effect, creating paradoxes that challenge our understanding of reality? These theoretical dilemmas add another layer of complexity to an already formidable challenge. For now, faster-than-light travel remains firmly in the realm of imagination and theoretical exploration. However, the very act of asking these questions pushes the boundaries of scientific understanding and keeps the spirit of discovery alive. As we ponder the possibilities of reaching other stars and galaxies, we are reminded of the vastness of the universe and the ingenuity required to explore it. Moving forward, let us consider another profound question that captures the imagination. How did the Moon, our closest celestial neighbor, come to exist? Now turning to the origins of the Moon, our closest celestial neighbor, we delve into one of the most fascinating mysteries of planetary science. How did it come to exist? The leading theory, known as the giant impact hypothesis, suggests that the Moon was born out of chaos and collision. Billions of years ago, during the early days of the solar system, a Mars-sized body, often referred to as Theia, is believed to have collided with the young Earth. The catastrophic impact would have ejected a massive amount of debris into space, which eventually coalesced under the force of gravity to form the Moon as we know it today. While this hypothesis is widely accepted, many questions about the Moon's formation and composition remain unanswered. For instance, one puzzling aspect is why the Moon shares such a striking similarity in isotopic composition with Earth. If Theia was a separate celestial body, we might expect the Moon's chemical makeup to include distinct elements from both Earth and Theia. Yet, the Moon's rocks are almost identical to those found on Earth, leaving scientists wondering if Theia contributed much material at all or if some other process was at play. Furthermore, studies of lunar samples collected during the Apollo missions have revealed unexpected complexities in the Moon's structure. For example, the Moon appears to have a surprisingly small core compared to Earth, adding to the mystery of how it formed. Did the violent collision strip away most of Theia's metallic core, leaving the Moon relatively depleted of heavy elements? Or could the Moon have undergone processes after its formation that altered its structure and makeup in ways we don't yet fully understand? Another intriguing question surrounds the timing of the Moon's formation. Some models suggest it formed shortly after Earth's birth, while others propose it happened much later in the planet's early history. Pinpointing this moment is crucial because the Moon's gravitational influence has played a significant role in stabilizing Earth's axial tilt, shaping our planet's climate and the conditions that allowed life to thrive. Beyond its formation, the Moon's origin story ties directly to larger mysteries about the solar system's early evolution. Was Earth unique in experiencing such a colossal impact, or could similar events have occurred elsewhere, shaping the moons and planets we see today? The Moon may hold clues not only about Earth's history, but also about the processes that shaped the young solar system as a whole. As scientists continue to study the Moon's surface, interior, and orbital dynamics using modern technology, we edge closer to unraveling this cosmic mystery. Yet, for all we have learned, the Moon remains a reminder of the dramatic forces that shaped our planet and the lingering questions of how it truly came to be. With the next phase of our journey in sight, let us turn our attention to another question that digs deep into planetary science. How do planets themselves form? Moving forward, we explore the captivating process of how planets form. It all begins within vast clouds of gas and dust, which collapse under the pull of gravity to create young stars. Surrounding these nascent stars are rotating disks of material known as protoplanetary disks. These disks are the cradles of planet formation, where particles of dust collide, stick together, and gradually grow into larger structures over millions of years. Eventually, these clumps form planetesimals, the building blocks of planets. The journey from dust grains to fully formed planets is a complex and chaotic one. As planetesimals collide and merge, they either grow into rocky planets like Earth and Mars, or gather massive amounts of gas to become giants like Jupiter and Saturn. But why do some systems create mostly rocky worlds while others produce gas giants or even frozen, icy planets? This is one of planetary science's biggest mysteries. The answer may lie in the unique conditions of each protoplanetary disk. Factors like the disk's temperature, density, and chemical composition play a critical role in determining the types of planets that emerge. For instance, in the warmer inner regions of a disk, rocky planets are more likely to form as lighter gases are driven away by the star's heat. Meanwhile, in the colder, outer regions, gas and ice can accumulate, giving rise to gas giants and icy worlds. However, these factors don't explain everything. Observations of exoplanetary systems, those outside our solar system, have revealed unexpected diversity in planet types and orbits. Some systems defy our current models, containing gas giants surprisingly close to their stars, while others consist of planets with highly eccentric orbits. What causes these differences? Could it be the result of chaotic interactions between forming planets, or perhaps the influence of nearby stars disrupting the disk's stability? Even within our own solar system, questions remain. What determined the specific arrangement of planets with rocky worlds near the Sun and gas giants further out? And why didn't Jupiter and Saturn, with their enormous gravity, disrupt the orbits of the smaller inner planets or prevent them from forming entirely? Advancements in technology, such as powerful telescopes and computer simulations, are helping scientists uncover clues about these processes. By studying young star systems and their protoplanetary disks, astronomers are piecing together the story of how worlds come to be. Yet, each new discovery raises further questions, reminding us just how intricate and varied the universe's mechanisms truly are. As we delve deeper into the mysteries of planetary formation, the next chapter beckons us to explore a protective force that shapes life on Earth and beyond. Why do some planets like ours have magnetic fields while others do not? With the next phase of the journey in sight, we turn our attention to one of Earth's most essential yet enigmatic features, its magnetic field. This invisible shield, generated deep within our planet, plays a crucial role in protecting life as we know it. By deflecting harmful solar radiation and cosmic particles, Earth's magnetic field preserves our atmosphere and safeguards the conditions necessary for life. Without it, the solar wind, a continuous stream of charged particles from the sun, could strip away our atmosphere over time, leaving the planet barren and uninhabitable. But how does this magnetic field come to exist? Scientists point to the geodynamo theory, which suggests that Earth's magnetic field is produced by the movement of molten iron and nickel in its outer core. As these liquid metals circulate due to the planet's rotation and heat escaping from its core, they generate electric currents. These currents, in turn, create magnetic fields which combine to form the planet-wide magnetic shield that surrounds us. Yet, as comprehensive as this explanation sounds, significant questions remain. Why do some planets, like Earth, have such robust magnetic fields while others, like Mars, do not? Mars, for instance, may have once had a magnetic field similar to Earth's, but it disappeared billions of years ago. Without its magnetic shield, Mars lost much of its atmosphere, leaving it a cold, desolate world. Was Mars's smaller size and therefore cooler core to blame? Or did some catastrophic event disrupt its internal processes, extinguishing its geodynamo? Even within our solar system, planetary magnetic fields show remarkable variety. Jupiter and Saturn have magnetic fields far stronger than Earth's, while Venus, a planet almost identical in size to Earth, has virtually none. What causes these differences? Is the size of the planet or its rotational speed the determining factor, or is it the composition and state of its core? The answers to these questions could provide critical insights into the broader processes that shape planetary habitability. Understanding magnetic fields has implications not just for Earth, but for the search for life beyond our solar system. If magnetic fields are essential for protecting atmospheres and sustaining life, then finding exoplanets with strong magnetic shields could help narrow down the list of potentially habitable worlds. But what methods can we use to detect magnetic fields around distant planets? And could there be alternative ways for life to thrive even without this protective force? As scientists continue to investigate these mysteries, the interplay between geophysics, planetary science, and astronomy is uncovering new layers of complexity. Each discovery deepens our understanding of the forces that mold planets and their capacity to support life. Moving forward, we examine yet another perplexing cosmic riddle. Where did Earth's water, the very foundation of life, originate? Moving forward, we dive into one of the most intriguing questions about our planet's history. Where did Earth's water come from? Water, the cornerstone of all known life, covers the majority of our planet's surface. Yet, its origin remains one of science's greatest puzzles. The leading theories propose two primary sources. Water could have been delivered to Earth after its formation, or it may have been present within the materials that first coalesced to form our planet. One of the most prominent ideas is that water was brought to Earth billions of years ago by comets and asteroids. These icy celestial bodies, rich in water and other volatile compounds, could have bombarded the young Earth, releasing their cargo upon impact. Scientists point to the isotopic composition of water on Earth, the specific ratios of hydrogen and its heavier isotope, deuterium, and compare it to the water found in comets and asteroids. The results suggest that some, but not all, of Earth's water may have arrived this way. Could a series of impacts spanning millions of years have gradually delivered enough water to fill Earth's oceans? On the other hand, some researchers propose that Earth's water originated from within. This theory suggests that water was already locked away in the minerals of the planet's building blocks, the rocky planetesimals that clumped together to form Earth. As the planet heated up during its formation, volcanic activity could have released this water in the form of steam, which condensed to form the oceans. If this is true, what does it say about the prevalence of water, and therefore the potential for life on other rocky worlds forming in similar conditions? Despite the progress made in understanding these possibilities, significant questions remain. If much of Earth's water did come from external sources, why does its isotopic signature not match that of most comets we study today? Could there be a yet undiscovered population of icy bodies that contributed to our oceans? And if water was already embedded in Earth's early rocks, how did it survive the violent, high-temperature conditions that characterized the planet's early history? The origin of water is not just a question of Earth's past. It also has profound implications for the search for life elsewhere in the universe. If water delivery via comets and asteroids is a common process, other planets and moons in other planetary systems might also receive water this way. Alternatively, if water is intrinsic to rocky planets, it could mean that liquid water and the potential for life is more abundant in the cosmos than we dare to imagine. As new missions venture to study comets, asteroids, and other planets, each discovery brings us closer to unraveling this primordial mystery. With Earth's watery origins in mind, let us turn our gaze to the rogue wanderers of the cosmos, planets that drift through the galaxy unbound by the gravitational pull of any star. Now turning to the enigmatic nomads of the galaxy, we explore the phenomenon of rogue planets, worlds that wander the vastness of space untethered to any star. Unlike the planets in our solar system that gracefully orbit the Sun, rogue planets drift aimlessly through the darkness, free from the gravitational pull of a parent star. But how do such planets come to exist, and what secrets do they hold about the process of planetary formation? One prevailing theory suggests that rogue planets are born like any other planet, forming within the protoplanetary disks of young stars. However, gravitational interactions, such as collisions with other planets or the chaotic influence of a massive neighbor, could eject these planets from their orbits, casting them into the emptiness of interstellar space. Another possibility is that rogue planets might form independently, directly from collapsing clouds of gas and dust, much like stars, but without gathering enough material to ignite nuclear fusion and become a star themselves. What makes rogue planets especially intriguing is their potential to host environments far stranger than anything we've encountered in our solar system. Even without the warmth of a star, rogue planets may retain heat from their formation or generate energy through radioactive decay, creating conditions where subsurface oceans or even life could theoretically exist. If so, could these solitary planets harbor unique ecosystems hidden beneath thick layers of ice or rock? Additionally, the discovery of rogue planets poses fascinating questions about just how common they might be. Could there be more rogue planets than stars in the galaxy? If so, what does that say about the processes that govern the birth and stability of planetary systems? The study of these wandering worlds is still in its infancy, but advancing technology promises new insights. Future missions equipped to detect the faint gravitational microlensing effects of rogue planets could reveal their prevalence and properties, shedding light on their mysterious origins. As we ponder these nomadic giants, we're reminded of just how little we truly understand about the cosmos. Moving forward, let's delve into the incredible life cycle of stars and the dramatic ways in which they meet their end. Moving forward to the majestic yet violent demise of stars, we uncover the mysteries of their life cycle and the breathtaking processes that mark their end. Stars, like living beings, are born, they evolve, and eventually they die. But how a star dies depends largely on its mass. Smaller stars, like our Sun, end their lives relatively quietly. After billions of years of fusing hydrogen into helium, they exhaust their nuclear fuel and shed their outer layers, creating stunning planetary nebulae. What remains is a white dwarf, a dense, Earth-sized core of carbon and oxygen that slowly cools over time, fading into obscurity. For more massive stars, however, death is a far more explosive affair. These giants conclude their lives in spectacular supernova, powerful explosions that can outshine entire galaxies for a brief period. In the aftermath, the core of the star may collapse further, forming either a neutron star or a black hole. Neutron stars, among the densest objects in the universe, pack the mass of the Sun into a sphere just a few kilometers wide. But when the core's mass exceeds a certain limit, not even the force between neutrons can halt the collapse, resulting in the formation of a black hole, a region of space where gravity is so intense that nothing, not even light, can escape. Yet, the exact mechanisms driving these supernovae remain an enigma. What triggers the precise moment of collapse and explosion? What accounts for the variety in supernova we observe? Adding to the intrigue are gamma-ray bursts, the most energetic explosions in the universe, often linked to the deaths of massive stars. Lasting mere seconds to minutes, these bursts release more energy than the Sun will emit over its entire lifetime. But their origins are not fully understood. Are they caused by collapsing stars, merging neutron stars, or something else entirely? These questions continue to challenge our understanding of stellar deaths. Despite all we've learned, the violent ends of stars still surprise us, hinting at the complexity and beauty of the cosmos. As we unravel these mysteries, we find ourselves drawn ever deeper into the wonders of the universe. With that, let us now shift focus to the intriguing cosmic puzzle of high-energy cosmic rays and their mysterious role in the universe. Now turning to the enigmatic world of cosmic rays, we encounter some of the most energetic particles in the universe. These high-energy particles travel through space at nearly the speed of light and constantly bombard Earth from all directions. Cosmic rays are primarily composed of protons, with a small fraction made up of heavier atomic nuclei and electrons. But where do these particles come from? Scientists believe they originate from a variety of powerful cosmic events, including supernova, the explosive deaths of massive stars, and active galactic nuclei, the energetic centers of distant galaxies. Some may even emanate from mysterious sources yet to be discovered. Despite decades of research, the full story of their origins remains elusive. Adding to their intrigue is the question of how some cosmic rays reach such incredible energies. While the majority are relatively low-energy particles detectable by instruments on Earth, a small fraction, known as ultra-high-energy cosmic rays, carry mind-boggling amounts of energy, far exceeding anything achievable by human-made particle accelerators. What processes in the universe could possibly accelerate particles to such immense speeds? One theory suggests that these particles are propelled by the shock waves of supernova explosions or the magnetic fields of rapidly spinning neutron stars. Another idea points to massive black holes at the centers of galaxies, which could act as natural particle accelerators on a scale beyond our comprehension. Yet, even these explanations struggle to fully account for the most energetic cosmic rays detected. What is equally puzzling is how these particles manage to travel vast distances through the universe without losing all their energy. Intergalactic space is not empty. It is filled with magnetic fields and cosmic microwave background radiation, which should, in theory, slow down these particles over time. And yet, some ultra-high-energy cosmic rays seem to reach us from regions billions of light-years away, defying our current understanding of physics. Despite their elusive nature, cosmic rays play a crucial role in the universe. When they collide with the Earth's atmosphere, they create showers of secondary particles, which can influence cloud formation and may even have a subtle effect on our planet's climate over long periods. They have also been instrumental in scientific discoveries, helping us study everything from the composition of distant galaxies to the fundamental properties of matter itself. Yet, their immense energy and unknown origins remain among the greatest mysteries in astrophysics. As we continue to study these energetic messengers from the cosmos, they may hold the key to understanding some of the most extreme and fascinating phenomena in the universe. With this mystery in mind, let us now venture into the intriguing landscapes of pulsars and the secrets they hold. Now turning to the fascinating world of pulsars, we find ourselves exploring one of the most extraordinary phenomena in the universe. Pulsars are rapidly rotating neutron stars, the ultra-dense remnants of massive stars that have exploded in supernova. These stars are so dense that a single sugar cube of their material would weigh as much as a mountain on Earth. What makes pulsars particularly unique is that they emit beams of electromagnetic radiation from their magnetic poles. As they spin, these beams sweep through space like the light from a cosmic lighthouse, creating a pulsing effect when observed from Earth, hence the name pulsars. The discovery of pulsars in the late 1960s marked a groundbreaking moment in astronomy. They were first detected by accident when radio astronomers Jocelyn Bell Burnell and Anthony Hewish noticed unusual, regular pulses in their data, which initially led them to jokingly consider the possibility of signals from extraterrestrial intelligence. These signals were later understood to originate from neutron stars spinning at incredible speeds, with some rotating hundreds of times per second. This discovery not only expanded our understanding of stellar evolution, but also opened new avenues for studying extreme conditions in the universe. Pulsars have since become invaluable cosmic tools. Their precise and regular pulses serve as natural timekeepers, more accurate than even the best atomic clocks on Earth. Scientists use pulsars to study the behavior of matter under extreme pressure and density, test the predictions of Einstein's general theory of relativity, and even detect gravitational waves, the ripples in space-time caused by massive cosmic events. Pulsars have also been used to map the galaxy and navigate spacecraft, acting as reliable beacons in the vastness of space. Yet, despite their utility, pulsars remain wrapped in mystery. How do some neutron stars become pulsars while others do not? What governs their magnetic fields, which are unimaginably strong and seem to drive their beam emissions? And why do some pulsars suddenly change their behavior, with their pulses slowing down or even stopping altogether, only to resume later? Additionally, the process by which pulsars emit their powerful beams of radiation is not fully understood, leaving scientists with more questions than answers. As we continue to study these enigmatic objects, pulsars promise to deepen our understanding of the universe. They embody the extremes of physics, providing a glimpse into conditions that cannot be replicated on Earth. Their behavior challenges our current models and pushes the boundaries of what we know about matter, energy, and the fundamental forces of nature. With their steady rhythms echoing through the cosmos, pulsars remind us of the precision and power of the universe's hidden mechanisms, urging us to uncover the secrets they hold. Moving forward, let us now turn our attention to the captivating question of whether life exists on Mars and the ongoing efforts to uncover this potential cosmic neighbor. Now turning to the intriguing question of whether life exists on Mars, we find ourselves examining one of humanity's most compelling aspirations, discovering life beyond Earth. Mars has long captured our imagination as a prime candidate for extraterrestrial life. Its proximity to Earth, as well as evidence suggesting that it once had water flowing on its surface, makes it a tantalizing target in the search for life. Ancient riverbeds, dried-up lakes, and minerals that form in the presence of water all hint at a time when Mars might have been a much more hospitable world, potentially capable of supporting microbial life. In recent decades, numerous missions have sought to unlock the secrets of the Red Planet. NASA Viking missions of the 1970s were among the first to search directly for signs of life, performing experiments on Martian soil. While the results were inconclusive, they laid the groundwork for future exploration. More recently, rovers like Opportunity, Curiosity, and Perseverance have scoured the Martian surface, analyzing rocks, soil, and the atmosphere for evidence of organic molecules and past habitability. The Perseverance rover, in particular, is equipped with tools designed to collect and store samples that could one day be returned to Earth for more detailed analysis. One of the most exciting discoveries in this search is the detection of methane in Mars' atmosphere. On Earth, methane is often produced by biological activity, leading to speculation about whether microbes could be active beneath Mars' surface today. However, methane can also be generated by geological processes, leaving scientists debating its true origin. Additionally, the European Space Agency's Mars Express orbiter and NASA's MAVEN mission have revealed evidence of subsurface reservoirs of water, further fueling interest in what might lie hidden beneath the planet's barren surface. Despite these advancements, many questions remain unanswered. Was Mars ever home to life, even in its simplest form? If so, what caused the planet to transform from a potentially life-supporting environment into the cold, arid world we see today? And if life still exists on Mars, where might it be hiding? Some researchers speculate that subsurface caves or underground aquifers could provide refuge for microbial life, shielded from harsh surface conditions like radiation and extreme temperatures. As we continue to explore Mars, the quest to answer these questions becomes increasingly urgent. Upcoming missions, such as those by NASA and the European Space Agency to retrieve Martian samples, as well as future plans for human exploration, hold the potential to make groundbreaking discoveries. Finding evidence of life on Mars, or even confirming its absence, would profoundly reshape our understanding of biology, evolution, and the uniqueness of life on Earth. With a red planet holding so many mysteries, it sparks not only scientific curiosity, but also a deeper reflection on humanity's place in the cosmos. Moving forward, let us now delve into the strikingly beautiful phenomenon of planetary rings and uncover why some planets in our solar system are adorned with these breathtaking formations. Now turning to the mesmerizing question of why some planets are adorned with rings, we venture into one of the most visually stunning phenomena in our solar system. Saturn, with its iconic, glittering rings, often steals the spotlight, but it's not alone. Jupiter, Uranus, and Neptune also sport ring systems, albeit less pronounced. These planetary rings are composed of countless particles of ice, rock, and dust, ranging in size from microscopic grains to massive chunks the size of a small house. But how do these rings form, and why do only certain planets have them? Scientists believe that planetary rings may originate from debris left behind by shattered moons, comets, or asteroids that ventured too close to their host planet's powerful gravity. In this scenario, the planet's tidal forces rip apart the incoming object, dispersing its remnants into a flattened, orbiting disk. Another potential origin involves leftover material from the early solar system, which never coalesced into larger bodies. These particles may have been captured by a planet's gravity, creating a ring system over time. While the mechanics of ring formation are fascinating, they raise a deeper question. Why are rings prominent around certain planets but completely absent around others? One key factor is the planet's size and gravity. Larger planets like the gas and ice giants have strong gravitational fields that can trap and shape debris into rings. In contrast, smaller, rocky planets such as Earth or Mars lack the gravitational influence necessary to sustain such structures. Additionally, the presence of moons can play a pivotal role. Moons act as shepherds, using their gravitational forces to maintain the structure and boundaries of rings, preventing them from dispersing or collapsing. This is evident in Saturn's system, where its many moons interact closely with the rings, sculpting their intricate patterns. Although rings are typically associated with gas and ice giants, their diversity remains a mystery. For instance, while Jupiter and Neptune have rings, they are faint and difficult to observe, making Saturn's bright, expansive rings an exceptional case. Could Saturn's rings be a relatively young feature formed from a unique event in its recent history? Or are we simply catching a glimpse of a fleeting phenomenon before the icy particles drift away or are pulled into the planet? As we continue to study these structures, each discovery deepens our understanding of how planets and their surroundings evolve over time. Planetary rings are not just celestial ornaments, they are dynamic systems, constantly changing and interacting with their environments. Their presence reminds us of the delicate balance and complexity that shapes our solar system. Moving forward, let us explore the enigmatic region known as the Great Attractor and uncover the gravitational mystery pulling galaxies towards it. Now turning to the mysterious phenomenon known as the Great Attractor, we delve into one of the most perplexing enigmas in cosmic science. Imagine a gravitational force so immense that it influences the movement of entire galaxies, including our own Milky Way, pulling them toward a specific region of space at incredible speeds. This gravitational anomaly, called the Great Attractor, has baffled astronomers since its discovery. Located roughly 200 million light-years away, this hidden region exerts such a strong pull that it affects the motion of galaxies across vast distances. But what exactly is the Great Attractor, and why is it so challenging to study? One major obstacle lies in its position, which is obscured by the dense plane of our galaxy, making direct observation difficult. This area, known as the zone of avoidance, is filled with stars, gas, and dust that block our view, forcing scientists to rely on indirect methods to investigate its secrets. Through detailed studies of galaxy motions and the use of X-ray and radio telescopes, researchers have begun piecing together clues about this enigmatic region. Some theories suggest that the Great Attractor is not a single object, but rather a concentration of mass, possibly a colossal cluster of galaxies and dark matter. Others propose that it may be part of an even larger structure in the universe, such as the Shapley supercluster, which contains thousands of galaxies grouped tightly together. Despite decades of research, the true nature of this cosmic force remains elusive. What makes it even more intriguing is its scale. The gravitational influence of the Great Attractor extends over hundreds of millions of light-years, shaping the large-scale structure of the universe itself. It raises profound questions about how matter is distributed across the cosmos and how unseen forces continue to govern the motion of galaxies. Could this anomaly hold clues to the very fabric of the universe? As technology advances and telescopes grow more powerful, scientists hope to unlock the secrets of the Great Attractor, revealing not only its composition but also its role in the cosmic dance of galaxies. With this gravitational puzzle in mind, let us now turn to one of the most perplexing questions in physics: the origin of the universe's missing antimatter. Now turning to the origin of the universe's missing antimatter, we delve into one of the most profound mysteries of modern physics. To understand this, we must first grasp the concept of antimatter. Imagine matter's mirror-opposite particles, identical in mass but with opposite charges. When matter and antimatter meet, they annihilate each other, releasing pure energy. According to the prevailing theories of the universe's beginnings, the Big Bang should have created equal amounts of matter and antimatter. Yet here we are, in a universe dominated by matter, from the stars and galaxies to the very atoms that make up our bodies. So where did all the antimatter go? The imbalance between matter and antimatter is a puzzle that defies simple explanation. Some scientists propose that shortly after the Big Bang, a tiny asymmetry in the behavior of particles and their antiparticles occurred, leading to a slight excess of matter that survived annihilation. This idea, known as CP violation, hints that the laws of physics may not treat matter and antimatter equally. However, experiments have only observed small amounts of this asymmetry, far too little to explain the immense dominance of matter in the universe. Other theories suggest that exotic processes in the early moments of the cosmos may have tipped the scales in favor of matter. For instance, interactions involving fundamental particles like neutrinos or hypothetical ones such as actions could have played a role. But without direct evidence, these ideas remain speculative. The search for answers continues to push the boundaries of both science and technology. Particle accelerators like the Large Hadron Collider aim to recreate conditions similar to those of the early universe, allowing scientists to study the subtle differences between matter and antimatter. Meanwhile, space-based observatories search the cosmos for traces of antimatter that might still exist in remote regions of the universe. Finding even a single antistar or antigalaxy could revolutionize our understanding of this cosmic imbalance. The stakes of solving this mystery are immense. Understanding why matter prevails over antimatter could shed light on the fundamental forces that shape the universe and even provide insights into why we exist at all. As researchers explore these questions, each discovery brings us closer to unlocking the secrets of the universe's earliest moments. With this enigma in mind, we now move forward to consider an even more speculative possibility. Could the universe itself be a sophisticated simulation created by an advanced intelligence? With the next phase of the journey in sight, we venture into a concept that blurs the line between science and philosophy. The possibility that our universe is a sophisticated simulation created by an advanced intelligence. This idea, often referred to as the simulation hypothesis, suggests that everything we perceive, space, time, and matter, could be the result of complex code running on an extraordinary computational system. While this may sound like science fiction, some scientists and philosophers argue that it is a hypothesis worth considering. One of the strongest arguments in favor of this idea comes from advancements in technology. As our own computational capabilities grow, creating highly realistic simulations of entire environments becomes increasingly feasible. Imagine a future civilization with technology so advanced it could simulate not just a small environment but an entire universe, complete with sentient beings unaware of their artificial origins. In this scenario, the simulated universes might outnumber the real one. If that were the case, the odds suggest that we could very well be living in one of those simulations. Supporters of this theory also point to strange phenomena in physics, such as the universe's apparent fine-tuning for life. The fundamental constants of nature seem to be precisely calibrated, as though someone had intentionally adjusted them. Additionally, the discovery of digital patterns within the fabric of reality, like the mathematical structure of space-time, has sparked comparisons to computer code. Could these patterns hint at something more? On the other hand, skeptics of the simulation hypothesis argue that it is fundamentally unfalsifiable. Without concrete evidence, it remains purely speculative, and many dismiss it as philosophical musing rather than scientific inquiry. Moreover, creating a simulation of this magnitude would require computational resources far beyond anything we can currently imagine, leading some to question whether such a feat would even be possible. Philosophically, the implications of living in a simulation are profound. If our reality is artificial, could the creators of this simulation intervene at any moment or reset it altogether? What would it mean for our understanding of free will, morality, and the nature of existence itself? Despite the lack of definitive answers, the idea continues to fascinate and provoke deep reflection. Whether or not we are living in a simulation, exploring this hypothesis pushes the boundaries of our thinking and challenges our understanding of reality. As we ponder these possibilities, we turn our attention to an equally intriguing mystery, the search for a new Earth capable of supporting life. With the next phase of the journey in sight, we turn to one of humanity's most pressing and hopeful quests, the search for a new Earth. Scientists have long been scanning the vastness of space for exoplanets, worlds orbiting stars beyond our solar system that could potentially support life. The focus is particularly on planets within what's known as the habitable zone, a region around a star where conditions might allow for liquid water, a key ingredient for life as we know it. Missions like Kepler and TESS have revolutionized this search, identifying thousands of exoplanets and bolstering our understanding of planetary systems. Among these discoveries are Earth-sized planets located within the habitable zones of their stars, tantalizing candidates for further investigation. Some of the most exciting finds include planets orbiting red dwarf stars, which are smaller and cooler than our Sun, extending the possibilities for life in unexpected places. Yet, despite these advancements, monumental challenges remain. Finding a planet with the right size and temperature is only the first step. A true new Earth would also need a stable atmosphere, the presence of water, and a magnetic field to shield it from harmful radiation. Even if such a planet is found, the issue of distance looms large. Most of the exoplanets discovered so far are located many light years away, making any attempt to reach or colonize them a task far beyond our current technological capabilities. This raises the question, would humans ever be able to develop the technology to traverse such enormous distances? Or would we need to rely on robotic probes and transmitters to explore these distant worlds on our behalf? Ethical considerations also come into play. If we were to find an exoplanet that meets all the criteria for habitability, what would happen if it already harbors life? Would humanity have the right to intervene, or would we need to develop new frameworks for interplanetary coexistence? While we still have much to learn, the search for a new Earth represents more than just a scientific endeavor. It is a testament to humanity's relentless curiosity and determination to secure a future among the stars. As we continue to unravel this mystery, it is clear that each discovery brings us closer to understanding not only the cosmos but also our place within it. Now turning to the enigmatic realm of black holes, recent discoveries have added even more layers to their mysterious nature. One of the most groundbreaking revelations comes from the detection of gravitational waves, ripples in space-time caused by cataclysmic events such as black hole mergers. These unprecedented observations, first achieved by facilities like LIGO, have confirmed that when two black holes collide, they form an even larger black hole while releasing staggering amounts of energy in the process. These events not only validate Einstein's predictions, but also unveil questions about how such massive objects form and interact. Were these black holes born from the collapse of stars, or could they be primordial, originating from the earliest moments of the universe? The idea of primordial black holes suggests that some may have formed shortly after the Big Bang, acting as seeds around which galaxies eventually coalesced. This leads to the tantalizing possibility that black holes may play a critical role in the large-scale structure and evolution of the universe. Furthermore, the study of these collisions offers insights into the otherwise hidden properties of black holes, such as their spins and masses. Intriguingly, some black hole mergers have raised questions about objects that challenge our current models, sitting in mass ranges that defy traditional astrophysical explanations. Could these outliers point to unknown processes or exotic forms of matter? Beyond their origin, black holes also appear to influence their surroundings in profound ways. Supermassive black holes at the centers of galaxies, for instance, are thought to regulate star formation and even drive the growth of galaxies themselves through mechanisms not yet fully understood. This interconnected role suggests that black holes may be more than cosmic anomalies. They could be fundamental players in shaping the universe as we know it. The quest to answer these questions continues to push the boundaries of human knowledge, reminding us of how much remains to be explored. With this, we turn our attention to yet another profound mystery of the cosmos, one that beckons us to unravel its secrets even further. With the next phase of the journey in sight, we dive deeper into the question of whether we are alone in the universe. Recent advancements in the study of exoplanet atmospheres have opened new doors in the search for extraterrestrial life. Scientists now have the ability to examine the chemical composition of distant planets' atmospheres, searching for telltale signs of life. These signs, often referred to as biosignatures, might include oxygen, methane, or other gases that could indicate the presence of biological processes. The discovery of potentially habitable exoplanets has further fueled this quest. These are planets that exist in the habitable zone of their stars, where conditions might allow liquid water to exist, a key ingredient for life as we know it. Fascinatingly, some of these worlds are relatively close in cosmic terms, such as the planets in the TRAPPIST-1 system, which orbit a star only 39 light-years away. But the concept of life itself raises thought-provoking debates. What exactly constitutes life? Could it exist in forms completely unlike anything on Earth, thriving in environments we might consider hostile? This broadens the search beyond Earth-like conditions to include extremophiles organisms that can survive in extreme environments here on our planet. If such resilience exists here, could it also exist on distant worlds? And perhaps the most profound question of all, what would it mean for humanity if we were to make contact with intelligent life? The implications of such an event would be staggering, reshaping our understanding of our place in the cosmos and challenging our most fundamental beliefs. Would such a discovery unify humanity in awe and wonder, or would it bring unforeseen challenges? These questions are no longer confined to the realm of science fiction. They are central to modern astronomy and astrobiology. As we continue to search for answers, the possibility of discovery beckons us forward, inviting us to explore not just the universe, but the very nature of existence itself. Moving forward, let us turn to another cornerstone of cosmic mystery, one that lies at the very heart of how time and space interact on the grandest scales. With the next phase of the journey in sight, let us reflect on the incredible mysteries we've explored together. From the origins of the universe and the enigmatic nature of black holes to the search for extraterrestrial life and the boundaries of the observable cosmos, each question we've pondered serves as a reminder of how vast and awe-inspiring the universe truly is. These unanswered questions not only challenge our scientific understanding, but also ignite a deeper sense of curiosity about our place in this cosmic expanse. Which of these mysteries captures your imagination the most? Do you have a favorite theory or a question that keeps you wondering? Share your thoughts in the comments below. We'd love to hear from you. Space remains an endless source of wonder, and while we may never answer all of its secrets, the journey of discovery itself is what makes us truly human. Make sure to subscribe to our channel and hit the notification bell so you don't miss out on more explorations into the unknown. Thank you for joining us on this adventure, and until next time, keep looking up and wondering, because the universe always has more to teach us.